When you think of explosives, what comes to mind? Probably just chaos, right? Pure, uncontrolled force. But what if I told you that behind every huge construction project, every mine, every single tunnel, there's this incredibly precise science dedicated to taming that chaos? Today, we're going to dive deep into the sophisticated engineering of commercial explosives.
So look at that number. That's the heart of the problem right there. When a chemical reaction travels at nearly 8 kilometers a second, how in the world do you make it predictable? How do you take that raw, untamed power and turn it into a precision tool? Well, the answer is all about understanding an explosive's fundamental properties. Okay, so to control an explosive, you first got to measure its power. And this really starts with three key things: how fast it is, how hard it hits, and how much work it can actually do. First up is what's called the velocity of detonation, or VOD for short. Now, think about it this way. This isn't the speed of the debris flying out. This is the speed of the chemical reaction itself as it rips through the explosive material. It's the number one way we measure an explosive speed.
And to put that into perspective for you, 7,900 meters per second is over 20 times the speed of sound. It's just an incredible velocity. But here's the really interesting part. Engineers don't always want the fastest explosion they can get.
And this slide shows you exactly why. A high VOD gives you this intense, shattering effect. Think of it like a sharp, fast strike with a hammer, perfect for breaking really hard, dense rock like granite. A lower VOD, on the other hand, releases its energy a bit more slowly. It creates more of a powerful heaving or pushing force. And that's way better for moving large amounts of softer material, like you'd find in a coal mine. So, tied directly to speed is detonation pressure. This is the sheer force of that detonation wave we were just talking about. If VOD is how fast the hammer is swinging, detonation pressure is the force of the impact. It's what does that initial, critical job of fracturing the rock. Okay, now don't worry about the numbers here. Just look at the letters. Pressure depends on density, D, and velocity, C. But notice that C, the velocity, is squared. That's the secret sauce right there. It means if you double the speed of your explosive, you don't just double the pressure, you quadruple it. This is probably the single most important lever an engineer has to control that shattering force. But raw power is only half the story. To use its safety, you really have to understand an explosive's personality, this whole set of characteristics that decide how it's going to behave out in the real world. This is all about safety, stability, and just plain reliability. First is sensitivity, and in simple terms, this is basically how touchy an explosive is. A really sensitive explosive only needs a tiny little impulse to set it off, while a less sensitive one needs a much more deliberate, powerful trigger.
So what makes an explosive go off when you don't want it to? Usually, it's about creating tiny little hotspots. A sudden impact can compress trapped air bubbles, making them instantly super hot. Friction can do the exact same thing on a sliding surface. And then, of course, there's just plain old heat. Get the whole thing hot enough and it'll detonate all by itself.
All right, now for something super practical, water. Because let's face it, a lot of the boreholes you drill in the ground are wet. Water resistance measures how well an explosive can hold up after it's been dunked. Some of the simpler explosives will fail almost right away if they get wet, while others are engineered to work perfectly even after being underwater for days. And these classifications show just how wide that range is. I mean, look at Class 1. It's rated to work indefinitely underwater. That's something you'd use for, say, a bridge demolition. But go all the way down to Class 7, and you've got less than an hour before it's totally useless. If your borehole is slowly filling with groundwater, choosing the wrong class means your whole blast is a complete dud. It's that critical. Temperature is another huge factor. Old school dynamite, for instance, could actually freeze, and that made it dangerously unstable. In contrast, modern emulsion explosives are designed to perform reliably and safely, even in sub-zero temperatures, which is just a massive leap forward for both safety and performance. The engineer's job isn't over once the button is pushed. In fact, some of the most important properties of an explosive are all about what happens after the detonation. A major concern is post-blast fumes. The explosion releases a lot of gases, and some of them, like carbon monoxide and oxides of nitrogen, are highly toxic. This is especially critical in places like underground mines or other areas without good ventilation, where these fumes can literally be lethal. And yup, here again, we've got a class system. A Class 1 explosive produces the least amount of toxic gas. So how do they do that? It's all about the chemical recipe. They oxygen balance it.
which is just a fancy way of saying they make sure there's just enough oxygen in the mix to burn up all the fuel. It's kind of like tuning a car engine for a cleaner burn to minimize the dangerous exhaust fumes.
Now here's a property you may not have heard of, hygroscopicity. It's simply the tendency of a material to absorb moisture right out of the air. And for an explosive, this can be a really serious hidden problem.
So what's the big deal with a little dampness? Well, that absorbed water just wreaks havoc. First, when the blast happens, that water flashes into steam, and that steals energy and cools the reaction, which makes it weaker. Over time, it can chemically break down the explosive itself or even corrode its packaging. It basically degrades the product from the inside out. So we've got speed, pressure, sensitivity, stability. Let's put it all together and see how these properties are used to achieve the main goal, breaking rock as effectively as possible.
It all really comes down to a 1-2 punch. First, you have that detonation pressure, which is driven by that super high VOD. That's the instant, violent shockwave that shatters hard material. But right after that, you get borehole pressure. That's the force of the expanding gases acting like a powerful piston. This is that heaving force we talked about, perfect for pushing and moving huge volumes of softer rock. This quote from our source material is the perfect example. ANFO, which stands for ammonium nitrate/fuel oil, a very common and cheap blasting agent, it has a relatively low detonation pressure. It's not a great rock shatterer, but it produces very high borehole pressure, which makes it excellent for heaving and displacing large volumes of material. It's a workhorse for exactly that reason. And that's the core takeaway here. Explosive engineering is a constant balancing act. You're trading shattering force for heaving force. You're balancing the need for immense power with the absolute necessity of control, and you are always weighing performance against safety. So the next time you see footage of a controlled demolition, or maybe you drive through a tunnel that's been cut through a mountain, remember, it's not just brute force at work. It's a complex, calculated science of speed, pressure, and chemistry. Which kind of makes you wonder, doesn't it? What other invisible engineering is quietly shaping the world all around us?